forward. Okay. You just make sure the camera's following you.
Okay. So shall we begin? Yes. So me and Akilan today will be giving a gentle tutorial on hardware description languages. We will start from some general concepts in hardware design, and we will be talking in specific about two modern hardware description language named Chisel and Bluespec. Feel free to ask me questions if you feel anything is strange. And I will begin by giving you an overview of the workflow in hardware design. And in the first step, usually we start from hardware description using these languages, and which will also be the focus of today's talk. But as you can see, we're actually still far away from getting our real hardware chip. So after you have your design, you need to test it through simulation, and then you can send it to different workflow tool chains. You can go to the ASIC tool chain, which will give you a real chip. You can also use FPGA tools to burn your design onto an FPGA chip. Such EDA tools will do a lot of detailed works for you to generate the real circuits. What I want to emphasize here is that in hardware description phrase, we're actually working on a kind of abstracted level or viewpoint on the hardware design. We're not working on the concrete thing. So that's what we should know when we are doing hardware description. So what is an HDL and what does it do? It describes hardware. And hardware is basically a collection or a combination of some basic components. I'm talking about wires, registers, or gates. And in the hardware description phrase, we are basically defining these components and we are connecting them to achieve the desired behavior. But also, since we are actually kind of far away from the real hardware design, there are something we are not doing during the hardware description phrase. For example, we are not specifying how we want to place these components in the real chip. So this is something we are not able to control in an HDL. And also, we're actually not specifying how these components will be implemented. I can give you an example here, which is a multiplexer, basic components in your logic, which takes a selection signal and picks one of its input to the output. And if your targeting devices has something like this as the basic components, then the EDA tool will happily map your logic into such things in a real chip or in your FPGA. But if the platform does not have such components, then the EDA tool will try to use other simple gates to generate this logic for you. Each will have the same behavior, but as you can see, this is not something we want or we care to control when we are doing hardware description. And since I guess people here are more from a software background, I will give you two examples to show the difference between hardware and software when doing similar tasks or doing the same tasks. And to make you a bit more interested in hardware. So here, the first example is taken from the AES algorithm, which is the standard cipher algorithm used in modern communication protocols. And here is one of the operation inside the algorithm. This operation works on an array, or you can see it's like a matrix, which has 16 elements. So 4 times 4. And each element here is basically a byte. So what does this operation do? It basically shifts the elements in each row. So for the first row, for the first row here, it shifts the elements by 1 element, by 1 position, and for the third one, 2 positions, third one, port 1, 3 positions, as you can see here. And if you are doing this in software, let's say in C, you might do something like this. You will iterate through this array and do some value changing inside that. That's what you would do in software. This is not super complicated, but you still have some work to do. But to implement this in hardware, it actually basically costs you nothing. Since we just want to do a mutation on these elements, we can just use wire to select the desired input and generate the output. So that's almost free. That's one thing that surprised me when I was first learning hardware design. And the second example, also taken from AES, is another operation which still works on this array. And for each byte inside this array, we are going to do a table searching. The table is called SBox. We use the byte as the index to the table, and we search the value out and replace that replace the byte in that position. And what you will do in software is basically define the table and do iteration and do table searching. That's what you will do in software. And as you can see here are actually some parallelisms. Since the 16 components, the 16 elements in the array, operation does not have any data dependencies, so they can run in parallel. And to exploit parallelism in hardware, we can directly define 16 SBoxes, each of them. So in this case, you can do all the operations in one go. This is how you achieve parallelism with hardware. And yes, that's my second example. And basically, that's for the general part in hardware design. And I will talk a little bit more about Chisel, which is a modern hardware description language. And it's embedded in Scala, a functional language. As I've mentioned, that when we are doing hardware design, we're actually working on an abstracted model. And here for Chisel, the abstracted model has a name called register transfer layer, RTL, which is the same thing for classic HDLs like Verilog and VHDL. I will talk a bit more about that later. And the advantages of Chisel is that it gives you better flexibilities and abstraction powers, since you are basically coding in Scala. And it has some useful libraries, and testing framework is easier to use. And also, you can compile Chisel down to Verilog or system Verilogs, since this is the input expected by almost all the EDA tools. So you can integrate Chisel into such infrastructures in this way. And I will directly give you a simple hardware module written in Chisel here, which is basically an adder. It takes two input and either do a subtraction or an addition to the two input and generate the output. If you look at the Chisel code, you can basically see. If you look at the Chisel code, you can basically see what we are doing. We extend from the module, which is a Chisel thing, and which means we are defining hardware, and we define the I/O ports for this module. So we have input, two input of the operands, and a 1-bit signal to indicate whether we are doing additional subtraction, and we give an output. And for the exact logic, there is a small trick, which is basically saying that A minus B equals to A plus negative B. And with this trick, we can use the same additional circuit to do both subtraction and addition. That's the small trick here. And the right-hand side is the generated Verilog code compiled from Chisel. And I'm using an online tool which takes the Verilog as input and gives you the diagram of your circuit. It kind of synthesizes the Verilog. And as you can see here, it's kind of straightforward. This is kind of straightforward. You can see your input, your 1-bit signal, and the 1-bit signal will decide whether to flip the bits of the second operand and add them, and add the additional +1 thing if you are doing the subtraction, and gives you the output. That's kind of the thing. And here is a cheat sheet of Chisel. You don't need to be scared by it. It basically tells you what primitives you can use in Chisel. For data types, there are booleans, which is basically a 1-bit signal, 0 or 1. And you have unsigned integers, which is several bits. And you have signed integers. These are basic data types. And based on them, you can construct compound data types, which is called a bundle. And in this case, you can have some simple abstractions. In the generated circuits, they will all be a set of 0-1 signals, but in your code, you can have some abstraction here. And the right-hand side is the operations in Chisel. As you can see, basically common operations you are expecting. And that's about the primitives in Chisel. Kind of simple and straightforward. Yeah.
So what is that notation, 32 dot W?
Okay.
What does that mean?
Any questions, can you repeat it to your microphone?
Okay.
Oh, sorry.
Yes. So Urian was asking, what is this 32W here, right?
Yep.
Yeah, the W is an internal data type in Chisel to specify the bit width of a thing. So this unsigned integer has 32 bits.
So 32 is injected into that data type.
Yeah. Oh. And for the final slides of Chisel, I will talk a little bit about its semantic. What we have seen for now are all about wires and gates, as we have seen here. These are all gates. And the wires and gates forms something called combinational logic. In the RTL abstraction, the register transfer layer abstraction used by Chisel, combinational logic is something that has 0 delay, and which means once you give the input of that logic, you will directly get the output. There are no internal states of that circuit. You can think of it like a pure function. So when you provide certain input, you are always expecting the same output with no delay and no internal state. If we do want some internal state, then we need to introduce registers. Registers is something that's able to store the state and introduce sequential behavior to a circuit.
Okay.
Yeah.
So you have like defined order like in previous slide. Could you use this like, yeah, I mean the earlier slide.
Yeah.
Yeah. Could you use this as a function, let's say when defining something else, like for example, defining counter, I mean, or something else, could you reuse it just like you have used max as a primitive?
Okay. In this case, we will need to instantiate an adder as a sub-module in a bigger module.
Okay, so it can be doable, like, yeah.
Yes. Yes. And for register, you can basically, it can be viewed as a simple hardware module, which has an input and gives you an output. And of course, the input and output should have the same data type. And it also takes a clock signal. A clock signal is a 1-bit signal that jumps constantly between 0 and 1. And the register in each rising edge of the clock, the register will update its output to capture the value of the input. That's basically the behavior of the register. And during the cycle, the value of the output will be maintained, will be held at the same. And the right-hand side is a stateful circuit using register. Here is basically a counter which increments by 1 in each clock cycle. And we are using a run signal as input to indicate that we want the register to we want the counter to run. And As you can see here, here is the inside logic of this module, which is also quite easy to understand. When the IO run is true, here we connect the input of the register to the output of the register +1. So we better understand this as a connection instead of an assignment, as you might do in C. That's not an assignment, it's a connection. Here is the generated circuit. You can see the connection. Here is the register, the counter register. And we are selecting whether we want to add 1 to it, and we will direct that back to the input side of the register. That's basically what we are doing.
So is the colon equals
Yeah.
special symbol in Chisel as opposed to Scala?
No, it's a Chisel thing.
Chisel, so it's not a Scala thing,
No.
it's a Chisel thing.
Yeah.
To say rewire.
Yeah.
Okay.
Connecting. Yeah. So that's basically all about Chisel. And as you can see, when you are working in this RTL level, RTL abstraction, when designing hardware, you are basically drawing the diagram in your mind. That's what you are doing. And this might feel kind of simple or straightforward at the beginning, but as the complexity of your hardware grows, this can be hard. This can be hard to maintain and design. So there are actually different languages and different ways of abstractions to view the hardware design. And I will pass this to Akilan to talk about a different.
Yeah.
Yeah.
But you can always take this, generate the VHDL output, and then visualize it, right?
Yes.
To kind of check, am I following what I expect?
Yes.
You do get some kind of feedback in that sense, right? I mean, it's. Or do you think in the end the code is easy to understand in the picture?
I will say if the code itself is easy to understand, then the figure is easy to understand.
Is there such a map? Is that always the case?
I would say maybe no. If your hardware design is complicated, the figure will be highly likely to be not able to read.
Yeah. So what I mean is, are there situations where
Yeah.
one of the two is easy, but the other one is not?
Hmm.
In the sense that, or is the mapping so one-on-one that you actually do have that?
I would say it's kind of one-on-one. If the code is complicated, but the figure is simple, this might suggest you are writing bad code. Yes.
Yeah.
Could the generated diagrams be used as a debugging tool for your code? If you generate a surprising hardware circuit,
Yeah.
is that a more useful debugging tool than, say, a compiler error?
Oh, I would say still, if the design itself is complicated, you might not able to draw much insights from the diagram. It will be also super complicated.
I have another question. So are there any restrictions on the kind of code you write within your class in the sense of generating? What if you have a big loop inside your inside the class itself?
Inside the class?
Can you have recursion somewhere that you, in the sense that it can actually not be described in hardware? Is that possible, or does the library impose certain restrictions automatically for you?
Okay, so what we essentially do inside this module is to specify the connection between ports. And if we are doing something like recursive functions, it will do. We can use higher order functions when we hope to work on something like a vector of wires. We can do something like that, but we need to be sure that what we are doing is doing wire connection. Otherwise, you might see something surprising that your logic won't be compiled into hardware. For example, if you look at this when statement, it's actually a Chisel thing. It's not an if statement in Scala.
Yeah.
If we're using an if statement, it's actually not the thing that we're compiled into hardware.
Yeah. But is there, because I can imagine that when people start to do this, it's kind of difficult to keep those worlds apart. But does the compiler or something help you? That as well, don't use this or that, because otherwise you get no hardware? Is that?
I would say the compiler is not this smart based on my experience. I do encounter some cases that the things that I wrote does not compile into hardware, but I guess you need experience for that.
If you were to write a function in your class which generates an infinite list of circuits, and then you compile it, when would the problem occur? When you tried to synthesize that infinite list of circuits, the Chisel compiler say that's an infinite list of circuits. I'm not going to synthesize the Verilog.
I'm not so sure about that. I'm actually not sure, since based on my experience, when you are doing something, it's simple to do something like a map on top of a vector of signals, which is kind of straightforward. But if you are something infinite, I'm not sure.
I guess it depends on the perspective which you come into this, right? If you are a normal programmer, you will be likely to use recursion, especially if you come, say, from a Haskell or from Scala. And then if you come out of VHDL, the world, then you will likely just use the primitives, but not necessarily start to use Scala features directly.
True. True.
So, and that's why I think it's relevant to kind of understand what will happen if you start to use Scala features that may lead to, or not, to circuits you can never work with. And I think this is what the 20 people did, right? They kind of simplified the Haskell to an extent that you could guarantee that the circuit could always be realized. And then I wonder what they do here, because this is an EDSL. It's not external. This is an embedded DSL. So you still have access to everything that Scala has.
True.
And then the question is, okay, is there a need for Scala, for the library to kind of restrict what you use from Scala? And if that is the case, who does that for you?
So that's basically it.
I have a question.
Yeah.
What are the pros and cons of using Chisel over Verilog?
Over Verilog, yes. If you are doing your hardware design in Verilog, the first thing you are not able to get is here. It's configurable width of your wires. You can do that in system Verilog, I believe, but in Verilog, maybe you need some other tools to help you do that. And of course, you can have higher order functions when you are working with vector of signals, things like that. So you can still utilize some Scala's power, but you need to make sure that they can compile to hardware.
Is it possible to like compose things in the sense that you could use the other platform? Is it possible to do that kind of thing in Verilog? Define something, then?
Yes, in that case, the thing you are reusing will basically be a sub-module of your top-level module.
That's also possible in Verilog as well.
Yes, yes. Okay.
Right. So now you can give a pretty good introduction to Chisel, I think, and I did like the last point when you mentioned about circuits in general. Like in Chisel, you look at it more in the viewpoint of a circuit. But now we're coming to Bluespec, and in Bluespec we look at hardware more in the form of functions rather than circuits. And there are two variants of Bluespec before we go inside. So there are two front ends of Bluespec. There's the Haskell front end, which is exactly the same AST as Haskell, for example, and you can actually even use the Haskell language server, for example, on top of it. And the second one is the Bluespec Verilog variant, which is more like Verilog, and it's a bit more imperative and has more of the object-oriented features in general. And Bluespec was basically written by two people, Arvind from MIT and Leonard, who we know from the Haskell community, who built the language, and it was open source just years back. And one of the key features which Bluespec has is what we call a rule-based design. And So with the rule-based design, it's, for example, we can basically write like conditions, and these conditions can be executed on every single cycle or run. And also we have like, it mostly focuses on higher abstraction, so you can use most of the Haskell features like type classes and even OOP paradigms like interfaces. And you can choose whichever front end you would like to use with Bluespec. And I can give like a nice overview of Bluespec. So we have on top the front end over there. What's interesting is if you use the Haskell front end or the Verilog front end, the actual backend is the same. So they're interoperable with each other. And you can basically write your implementation on the front end, compile, use the DSG compiler, and you can, of course, compile it to either the Bluespec simulator, which is built by the maintainers themselves, or you can compile it down to Verilog. And today we'll be working on the RTL simulator when we're doing our demo. And so you can also, similar to Chisel, you can run it straight on the FPGA. So the concept is the same in that viewpoint. And so you can give an adder example in Chisel. Let's talk about an adder example in Bluespec so we can see how different they are. So when we're implementing an adder, we can, first of all, easily just define an interface, which is rather trivial. And it's basically the shape of the function. We say we'll take two inputs of 32 bits each, A and B, and we give the output, we return an output of the 32-bit. And we have on the right-hand side, we can define a module, we call it make top, for example. And we have, for example, the action value down there, which basically will basically is the same shape as the interface, and it just takes two parameters, for example, A and B, and we can do an addition and return the output. And the do-add function is on the top there that does X plus Y. But of course, I did realize while we were making the slides, in reality, you could have just done X plus Y under here, and we did not require that extra function on the top. But as you can see, in contrast to Chisel, Bluespec is a lot more in the high level and a lot more easier to write, more programmer friendly. And as you can see, it generates the Verilog as the output, which is just a very simple adder. It's two inputs and gives an output.
So, question about your adder. I try to read the syntax, intuit the syntax. So it says an action value, then it says bit 32. Does it mean that this is because it doesn't say anything about parameters really, right? Because you name parameters below that.
Yeah, well, that's like the return type. Bit 32.
Yeah, okay, so that's the return type. Okay. Yeah.
Right. And then the other two are the parameters.
Okay, but it feels a bit strange though that you don't declare your arguments, you just use them, and that is an implicit declaration of an input. Is that right?
I think so, yes.
Okay. So there's no binding, you just use it.
Well, we actually, yeah, we import the interface as well.
But that's a synthesized code. That's not.
Yeah, this is just a definition of.
I'm looking at the code that a programmer writes and understands, right?
Yeah.
It's not an EDSL in Haskell, right?
No, it's a separate implementation.
So external DSO.
Exactly. So we can now even give a comparison between, for example, Chisel and Bluespec in a way. So, for example, Chisel, you can see you can even define like a multiplexer. So you can define more things in detail. So you can also define concurrency in Chisel, I believe. But whereas in Bluespec, it's a lot more high level. The concurrency is automatically generated by the compiler itself. And that means, and also Bluespec works on, like, for example, rule base. So for example, you can run each rule independently at compile time, so they can catch, like, I remember the question you asked about, and Rob mentioned about catching loops, or for example, in my previous code, if I had written like 16 over there, the compiler would catch and say, this is incorrect. Well, it will raise a compile time exception. And this is like one of the benefits of using Bluespec over, for example, Chisel or Verilog like RTLs. Of course, that means you cannot represent certain things on, like, you can't define concurrency, you can't define certain actions you can do it on a cycle level. So that's the limitation of Bluespec in contrast to languages like Chisel. And
I find it odd that you say you can harness concurrency, but performance properties are not
Yeah, and when I mean,
possible. I mean, so on the one hand, you say, well, I don't have a lot of control, but you can still harness concurrency. How does that?
so they mean harness concurrency, that means the compiler will generate it for you.
Yeah, but it depends on the cleverness of the compiler.
Yes.
Right. Yeah. So, and
Technically, yes.
so you don't harness it. You're lucky if you get it.
Sure.
What do you mean by non-deterministic here?
Um,
What's I don't like understand. So the other thing is like deterministic. In what sense?
I think that might because the compiler needs to control the rules for you. So at your code level, it's not a one-to-one map directly to the circuit, which is it's not this.
yeah, as you can said, the compiler will generate the rules for you. For example, even does the scheduling for you.
But it's non-deterministic. I mean, it's a bit comparable. I think if you have a compiler, like say Haskell compiler, then you don't control the optimizations it does, right? But it's not non-deterministic. It's something that it's not transparent.
Yeah.
I think that is maybe the notion. Yeah. Because if you run the same compiler with the same rules and the same input, you do expect the same output, right?
Yeah.
Okay.
Yeah.
So when you're saying non-deterministic, do you mean the generated circuit could be different each time, or the functional outputs of that circuit are non-deterministic?
I think neither.
Either. I mean, the circuit will be the same as generated, but I think, as Yukang said, the rules we can't control the rules.
Yeah, I think it's just not transparent. It's the same if you compile Haskell, you don't exactly know whether, for example, Haskell can decide whether a value is strict or not. Depends on the cleverness of the algorithm.
So what you mean is that your rules that you've written at your source code level might be compiled away, and you don't know if that's happened.
Yeah, exactly.
Things like that. So it's a bit, it's unpredictable for us.
Yeah.
Because we don't know exactly how the compiler works.
Exactly.
And a new version of the compiler might work differently.
Exactly.
And this doesn't happen in the case of verilog/RTL.
No, I think it's because they define it.
It's one-on-one.
And so before we go to live demo, we're going to also use a concept called pipelining. So as you can see here, we have register A and register B, and you can do combinational logic that can be a chain of additions, a chain of subtractions, and so forth. And in an ideal world, we would want to, within the same clock cycle, if I also do like a bunch of operations, and also, for example, we would want to write register A to the combinational logic, and then immediately also read to register B, for example, output. But in reality, this takes a bit more time than we expected. So, for example, as you can see here, we are reading the output of register A, doing some operation like addition, subtraction, multiplication. And when we want to, for example, write to register B, for example, we are at a state where it's operational. So I'm not sure what's the term you use, Yukang, for.
When register B needs to capture the value on its input. Yeah,
exactly. When register B wants to capture the value of its input, we can, because it's at an unstable state, if I'm phrasing that right, read. So this is particularly a problem we have. And we have two particular solutions. One is lowering the clock frequency. And then in that case, maybe this one will be a bit more expanded over here. So it's not an unstable state. So we could, for example, do registers B's operation as well directly. But the reality is, when we do lower the clock frequency, it takes longer time to execute an instruction. So that's bad in terms of performance. But another thing we can do is also insert registers in between a certain combinatorial logic, and that is basically pipelining. So, for example, down here, I can read from register A, do something, write to register B, and again read from register B, sorry, read from register and write back to register B. And this is basically pipelining where I can maintain the same clock frequency or even have a higher clock frequency and then do more actions at the same time. And we're going to do some live coding right now. Presume. And we're going to do today something really, really simple. We're going to take two inputs A and B. And for example, we're going to do an addition. We're going to write to the register. And then we're going to do a bit flip of that output and then write it out. And me and Yukang will do it in different languages. You want to start?
Okay, yeah.
So big flip here means you flip all units.
Yes. So in reality,
The same thing.
the operation here is very simple. So we actually don't need to pipeline it, but we are doing this for demo. Emacs and write chisel code here. So I will want to split the adder and bit inverter into separate modules. So to give you a feeling of how do we build a bigger modules from smaller modules, as Matthew has mentioned. We extend module and we define the I/O port.
Two things here. There's a typo in the word with. And the second thing is this Emacs language server for Scala or for Chisel?
For Scala. Yes, we install integer with the configurable. Yes, sit here. Need a W here. Similar thing for the second operand. We'll give the output. So this will be the I/O of the module, and the logic is very simple. The output will be our adder. And for the bit reverter, let's call it. Let's also make it configurable. Extends for I/O as a single input and a single output. So this will be the I/O, and here the logic is also simple. It's as the two sub-modules. And for the top level one, we want to build a pipeline.
Just ask a question that you asked earlier.
Yeah.
That capital W, I mean, to me, that reads like a field within the type int, but what is the capital W meaning?
Okay, it converts this integer, since this width is an integer. It converts this integer into a width type. So this whole thing will be.
I guess everything is object oriented, so it's kind of like a conversion that takes an integer into a W value. I find the notation a bit odd, but yeah.
Okay, now, yes, we want to use submodules inside this top one. So what we do is we define the submodule. We instantiate it here as a module. Pass parameter for it. So that will be the first one and the second one. Yes. And now what we want to do is to connect the input, to provide the input of these submodules. So for adder, IO, A, we connect it to the input of the top module. The second one, we do the same. Okay. And now we need to define a register to hold the output of this adder. So let's call it adder's result. Let's define a register next to adder. Yep. And now we will send the value of this register as the input of the flipper. So for flipper, input will be connected to adder address, adder result. And for the whole module's output, it will be the flipper's output. So that's basically all.
Yeah, some questions.
Yeah.
Is there a reason why you introduce adder res at all?
Adder res is a register. We are using a register in the pipeline.
Okay, so you cannot directly connect rec next to flipper IO in.
If you do this, then it will be no register. The whole thing will be a combinational logic.
Ah, so this makes the pipelining explicit.
Yes.
The fact that you use an intermediate register, but you don't. I find it a bit odd because you don't declare it. For me, they're just variables in Scala. They don't feel like a register.
Okay, so this is actually a register. One thing I feel a bit strange is that in Scala, the register's type is also int, unsigned integer, instead of a register type. The type system in Chisel is actually kind of strange to me, but I don't know.
That feels a bit odd. Okay, but yeah, okay. So so interestingly that in a normal programming language, it wouldn't make a difference whether you use this
True.
or whether you do it directly. But in this case, for the generated circuit, it does make a big difference, right? Which I
True.
don't think it's very insightful.
Mm.
As a for the, not you, but not what you do, but the technology itself. Because I think it would be better to make that explicit.
Okay. You can actually program in a more explicit style. For example, you can define a register. Name is address res, and you explicitly connect this to the register. Right. And this one is kind of a
Shorthand.
yes, yes. And at the end, we will.
Another thing is if you would say vol a comma b equals input, is that okay?
Where?
Well, because what you often see, you get a lot of these, I would say boilerplate code, right, when you write this.
Mm-hmm.
For example, if you do vol A and the vol B, could you kind of combine that? Say vol A comma B equals input uint with W. Is that okay? Or
I think
okay.
You know, one thing to help you save some lines of code is when you are defining multiple I/O ports which has the same type, you can define this bundle as a top level class.
Oh, right. Because I mean, first of all, I think this becomes awkward, but I think it's also that you always want that all of these things have the same width, right? Typically.
True.
But you always have to say it. So you might accidentally write one wrong.
Mm-hmm.
I'm not sure what happens in the type errors, if there's any.
The compiler will capture that.
Okay.
Yes. But I actually think this is not part of the type, since the type is integer. There's no value inside that type if you look at this. So I'm not sure.
So what if you would declare this as a different width, like with times 2?
Okay, so let's say you are doing something like this, right? Doing something like this?
Yeah.
Okay, so we can try to compile it. I would think that the problem will happen here since the width of the tooth thing.
Yeah, okay. Not when you add stuff,
True.
but when you connect the wires up because they don't align.
True.
Yeah.
But I remember Chisel seems to allow you to do that, but we can try. Yeah. So
Let him read it first.
So in the main function, we will send this pipeline module to a Chisel function, which gives you Verilog. And here we will give the width here, so 16 bits. And we can run that.
Bigger font, please.
So then you can.
Bigger font in the terminal.
I think the font is the same.
You can do Control Shift and Plus.
Okay.
Let's speak.
If it compiles, it will be a bit.
If it compiles.
Since we are okay, it compiles.
Yeah,
So
maybe-
Chisel allows
you
you.
never know, right? Maybe because it might accidentally be able to pad stuff. You don't
Yes.
know that.
Chisel will allow you to do this. So if you look at the generated code here, these things are 16 bits. So this is the Verilog.
And line 18 is 13 bits.
So the pipeline here is 14. So 0 to.
Yeah.
And
But if you connect it up,
it allows you to do the connection.
Yeah.
So I guess that's,
it might be, yeah.
yeah,
You know, I don't know what.
yes. I
maybe
think
some kind of defined behavior in Verilog for this.
sometimes you will want to use this. For example, you are only interested in the some parts of
Yeah.
a signal.
But would it also then, is it then some, would it work the other way around?
Uh,
So if you would have increased to,
yes. Let me try. So here.
Yeah.
We are going to compile this.
because to some extent it's a bit weird that they have you kind of write explicitly all these widths and then they don't check for it. That's odd. Why would you do it? No, for yourself, maybe.
Works. So if you look at the Verilog, no,
Yep, 17.
True.
But it has only generated the Verilog. Now, what happens if you use the generator, if you would use this Verilog in a simulator or whatever, right?
Yes.
Then it might start to complain.
Oh, okay. So I think I think the EDA tool will take this and it will simply ignore those.
Yeah, but for example, how would it know which ones, right?
That
The most
usually
significant, the least significant.
usually the least significant are preserved. Usually. Yes. So the final thing we can do is to send this to this tool. It gives you the line.
Just as a comment, I think that's very interesting and useful.
Mhm.
I feel like Emacs is dying out for a preview pane, like a chisel mode, which allows real-time regeneration. It's a bit like with LaTeX mode, where you can generate the math in a separate Emacs buffer. It feels like somebody needs to build an Emacs mode for Chisel, which doesn't require you to go to a website,
Mhm.
and it's in a buffer as a kind of debugging tool, which is maybe more useful than a compiler warning.
Okay.
But it is running now, right?
Yes. So if you provide input here, you actually get output. So it's actually a small simulator. Things here.
Would be difficult in Emacs.
So this is the output. And you can see the internal value, something like that. So that will be the chisel part.
So you can, does Chisel allow you to specify when defining a class?
Mhm.
Can you specify two widths, like width 1 for input and width 2 for output? Like you have only one parameter there.
Yes. I mean, the class with the same name but different types of.
That's width 1
Uh-huh.
for input and width 2 for.
Yes, you can do this.
Okay.
You can do this. So that's basically the chisel part. And Akilan will share his screen.
So, we're going to do the same thing Yukang did, but we're going to implement it in Bluespec, and maybe we will try to change some register sizes to see if it's going to catch or not.
Sure it will.
Turned out.
Haskell loves
I've just basically created a basic folder called source BSV, which is just a folder, and we have a make file which is on the outside, and it'll basically call this Bluespec file we're going to build and give us a Verilog output. And we're going to do the same thing Yukang does. We'll paste our Verilog output in the simulator online and see the difference in the circuit generated from our implementation. A file called pop. And we're just going to put them in. I'm just going to find a page and then I'll
Attach the
Sorry? Yeah. I'm just going to find my package top. So this is basically just a new package we've created, and we're going to create now our little interfaces as we showed previously, and that will just be is it's in method type action value. I'm going to pass in my output right now. It's going to be 32 bits as our first output. And we're going to now we're going to call our interface, for example, the function inside it called run. Inputs for the run function, which will be also
the method name is run.
Yes.
Action value being a keyword in DSV.
Yes, it'll be the action that will run in the simulator.
What's the meaning of action value as a keyword? What is it?
From my understanding, it's when when we define the function below, you will see that it will do the addition, then it will write to the register and do the next section as well. So that was my understanding what action value means. I think as we write more, it will become a bit more easy to understand. And we'll define our interface, and now we're going to define our module. Okay, top. I'm gonna say that change this So input of module. We have right now defined our module as well. What we're going to do is first we're going to define our a new register we want to create. So we're going to define that as a 32-bit register. As an output, be the module register. 0 just means like the default register. Now I'm going to create our first function when we're going to call that our addition function. So the output as a 32. That's the output, and we are going to do, I'm going to call it to add example. With 2 inputs, 32 bits.
So Akilan, I have a few questions. So you don't uniformly follow the usage of hash. For example, hash at the beginning. I mean, bit doesn't have a hash in front of it. I mean, after that in the beginning, then you have like hash followed by bit, then hash before bit.
That's why he has a compiler.
Okay. Yeah. So
I hope the compiler will tell him.
okay. Okay. So it is supposed to be uniform.
I don't know if it's supposed to be uniform. We
Yeah.
don't know
Yeah.
yet.
That was my question.
The compiler will tell him.
I don't know if I've written it correctly or not in the end. You caught a mistake I did.
Yeah. I mean, I was just asking whether it's. I was trying to understand what does that hash mean, and yeah. No. Yeah.
Let me call this. We'll basically just return plus y, for example, just a very simple addition. Do the same thing. Using one parameter. Basically, the sign just means the bits or the parameter x passed in. Now we're going to create our method. We're going to create a method called action value. Two bits as our output of that function. We're going to follow the same shape as the interface we defined. Call that run because we need to just run over there.
So the fact that you've put if c run as the round bracket argument to make top module, is that almost in Java saying make top implements the interface called if c run?
Exactly, the same thing. We're going to now just call the function to add. So inside a method right now, we've just called the function to add, and we're going to write it out to a register right now, and it's rather simple to do that. So we named our register out, so we just have to We just have to just call out, and if I do it's basically this notation that's equivalent to just writing out the register out. And after we've done this, we're going to now just do the bit flip of that. So I'm just going to do a return, and I'm going to call the function bit flip. And I'm going to pass in the value, the output of the register. So I think I've done some mistake here, but when we compile, hopefully it's going to scream and tell where we.
Exactly.
All functions have to be combinatorial, no use of registers.
There is user register here.
In the functions,
The functions itself.
you add bit flip.
Yeah.
If you try to write to a register in one of your two functions, is that permitted?
I could do that, yes.
So what's the difference? Okay.
I just wanted to make sure, like in one function, we could show as writing. We could do all this in one function. We don't have to separate ones, but just to give a feel of the language.
You cannot compile it in this. You cannot syntax check it inside the environment.
Here.
Yeah.
So the funny part of Bluespec is there is one implementation in Emacs which has a good language server written. Even that is like it's not maintained that often as expected. So they still don't have many features to, for example, syntax check. The best bet is rewriting this in Haskell, the Haskell version, and then using the Haskell language server as your checker to catch. So that's what I think people are trying to do these days as well. But this is not the Haskell
We're
version.
just talking about syntax checks, right?
Like,
If you change it into Haskell, then it's not this syntax anymore.
yeah, it's a different one. But you mean like if there's a mistake, like a red color?
Yeah, I'm pretty sure there's a mistake in here. So I wonder why can you not catch that here? I would expect you to be able to catch that here and whatever.
It's probably the
Visual Studio doesn't understand essentially the syntax of this language.
library, the VS Code extension I'm doing does not understand it.
There's one thing to have type errors, but at a much shallower level, there's another which is to have knowledge of the syntax of the language.
Yeah.
And I think the question is where are the red squiggly lines, even just for syntax. But it looks like VS Code doesn't even understand spec log syntax, regardless of the underlying type checking that might occur later.
Oh, that's too bad.
Very, very frustrating, but yeah, catch it.
Oh yeah.
Or so I did suspect I did something wrong there.
I think there is a hash in front of hash after bit.
But it's fine.
After the letter T, bit.
Even here.
I mean, you always have a hash after the bit, and it does that one you don't. I don't think the error message says that.
Doesn't say that, but you're right. It says unexpected. Okay, that was the error. Okay. I can do before I run that. I can do something where we can change the value to 16 over here. For example, to see if it catches.
Yeah.
And it should. give an error.
Ah.
So we do have.
But, well, true. But I think one thing that is also that you have fixed everything to 32 bits,
Yes.
while Yukang's was parameterized over the width.
So that is my bad implementation. I could have made it more.
But you can make that.
I can make it like that. That was just me. Parameter.
Yeah.
Parameter.
You can redirect it now.
I was going to directly paste it on the online editor.
Oh, right. You need to copy it.
If you run it, this is our generated circuit from Bluespec,
Oh,
which is very different.
yeah.
From things.
Yeah.
We don't have much control as Yukang does, so we leave it up to the compiler to generate it. As you can see, it also added two muxers out of nowhere, but I remember in Chisel, you have to define that as well.
Muxers?
Multiplexer, sorry.
Oh,
Nothing wrong.
Okay.
Okay, is there any questions or shall I give a run of the?
well, I mean, can you compare performance? Is that easy to compare between the two? I mean, yours looks different clearly, but maybe this is faster. I don't know.
You can see the timing. Their timing is actually the same. The additions result will go to the register, and the registered output will go to the flipper and be the output. The two things added here is basically one is the reset signal, one is an enabling signal added by the Bluespec itself, but it does not interfere with the performance of the whole.
No. It's more like how it's embedded in a particular context.
True.
Yeah. Okay.
So one thing you're not demonstrating is the rule-based features of BSV.
Yeah, so this demo we've not implemented that just to keep under time constraint.
But Akilan, do you write the rules?
You can if you
Do you work with the set of rules provided by the compiler? How does that?
so you can so for example back in the
You don't have to show it, but
so you can write this thing called rules and you can say, for example, if register A, if the value is greater than something, then you can execute some sort of action. So that's what they mean by rules and can fire on every cycle.
this is a bit like runtime instrumentation, compile time instrumentation. So I think Haskell has that as well, these rules where you can kind of say, well, whenever you see this kind of code, transform it into this code.
Yeah, it's exactly like that, but more for hardware.
The GNC has that as well.
Well, what can they pattern match on? So value dependent rule-based firing, i.e. the value inside a register is greater than 5.
Yeah.
But what other things can a rule in BSV pattern match on? Can they pattern match on time or a given clock cycle, or what are the things that they can pattern match on?
So I'm really not familiar with the scope of the rules with BSV, but I'm not that familiar to know exactly. It's something interesting to look up.
Just out of interest, can you try to assign to a register in one of your functions? Because I'd be surprised if it compiled and checked.
So you need to assign a value to the register.
Yeah, just break one of your functions to randomly write something to register out, not before the return statement.
All right.
You want like some sort of random value, like
Yeah.
12.
Does that type check?
Why not? It's in scope. Oh, but it's in a different mode.
Yeah, functions.
Yeah. Yeah, it does. Yeah.
Yeah.
So my understanding is that a function is combinatorial. It's pure.
Yeah.
It maps outputs from inputs only.
Yeah.
But it doesn't have the stateful behavior of a method. If you need state, use a method.
Yeah.
You want utility functions, which are kind of linear combinatorial logic blocks. You can use a function.
Exactly.
And the only benefit of a function in this context is code reuse. You don't have to write this code lots of times. You can write it once.
Yeah.
But apart from that, it doesn't have any kind of deep hardware functionality. It's just boilerplate. Yeah.
Yeah.
Exactly.
Okay. So we can do a demo of the circuit to see if it works. So I will change the value 16 over there. And I can do my first one. I believe, I don't know if it's big enough, but you can see that it's done. Let's put the output here.
44.
No, that's a decimal. Sorry, I did it in hexadecimal.
Ah, right.
The values off.
Right.
Refire it.
Yeah,
Right.
but your input is that hexadecimal.
Yeah.
22 plus decimal. So now it should be. So now it's 50. Now it's 56 as decimal.
Yeah, exactly. So our addition works, and we can do our reset. Well, it passes it on here as well. If I do the next clock cycle, so we can see that's our binary value. You can read the BIN. It's 1111000, and after we go through this,
Yeah.
inverted,
Yep.
and written back here. So this is our output of using Bluespec when building the pipeline. Any more questions? I think.
Yeah, thanks.
You want to stop?
Please. See you, Hans Wolfgang.
I guess Hans had no questions.
I can stop it.
Can you?
Yeah.
I'm seeing how to stop it. Record. Ah. Stop.